Hello everyone, I am Nicola D'Avanzo. I am a PhD student from University of Milan in Italy, and I will present to you a work titled Experimental Evaluation of Free Interaction Channels for Accessible Digital Musical Instruments, which I wrote with my supervisor, Federico Vanzini. In this work, we present an experimental method for the evaluation of physical interaction channels suitable for hands-free musical instruments. I'll give a brief introduction to what ADMIs are and what we mean by hands-free ADMIs. I will then expose some questions about the evaluation of physical interaction channels for hands-free ADMIs, bringing some examples and showing some related issues. I will then talk about our experiment, carried out with the described method, and discuss the results. Let's make a brief introduction to ADMIs. ADMI stands for Accessible Digital Musical Instrument. There are a lot of terms involved in the context of ADMI's design. Accessible indicates an instrument dedicated to people with disabilities. Assistive relates to the fact that an external source, namely technology, provides an aid to a person with disabilities. Adaptive refers to the ability of an instrument to adjust the context and the needs of the musician. Digital musical instruments, or DMIs, have the potential for augmented accessibility with respect to traditional ones. Due to the exponential increase of computational power, miniaturization, and unavailable sensors, research on DMIs has expanded during the last 2 decades, making ADMIs possible. They've carved out an important space in literature, giving also birth to important review works, such as Fritz, which reviewed 114 instruments. ADMIs include instruments aimed at different types of disabilities. However, our project is dedicated to physical disabilities, in particular those that preclude the use of limbs. We refer to these instruments as hands-free ADMIs. The main stakeholders are quadriplegic musicians. All the interaction channels located on the head and neck can be exploited to control such instruments, if we can detect them using sensors. There is already an amount of ADMIs exploiting such channels, like the high note, the high harp, and netitar in the images from left to right, which are free instruments which exploit eye tracking or head movement. But what do we mean by physical interaction channels, and how can they be evaluated? With physical interaction channels, we indicate any type of interaction channel detectable by sensors. Most of the traditional musical instruments, such as pianos, guitars, and flutes, mainly employ 3 channels: hands, breath, and feet. Instruments dedicated to quadriplegic people can instead employ, for example, the eyes with the movement of the gaze and eyebrows, the head with its degrees of rotation and muscle tension, the mouth detecting its aperture, bite pressure, tongue movement, voice, and breath. The mind also. Through an electroencephalogram, it is possible to detect different parameters that can be used for interaction. The purpose of our experiment is to analyze 3 of these, which I will now review. The first channel are the eyes, in particular gaze pointing. Gaze pointing is a consolidating interaction channel in the literature and often used in accessible technologies such as writing tools, but also in musical instruments such as the eye harp, in the bottom right image, entirely controlled by the gaze. We evaluated gaze pointing using a commercial infrared eye tracker famous in this field, the iTribe. Breath pressure has a natural relationship with sound intensity in the voice and in wind instruments. In the field of assistive technologies, it is often used as a control method for wheelchairs through sip and puff sensors. In order to evaluate breath in our experiment, we built an ad hoc sensor using the Arduino Uno microcontroller, interfaced with a low-pressure sensor connected to an air tube and an interchangeable mouthpiece. The third and last channel we evaluated is the head, with its 3 degrees of rotation, yaw, pitch, and roll. There are various ways of detecting head movement. 3D camera-based trackers or head-mounted sensor can be used. For our experiment, we built an ad hoc head tracker based on Arduino Nano microcontroller, interfaced to a module including an accelerometer and a gyroscope, both mounted on a headphone set. What do we mean by evaluating these channels? Evaluating and comparing musical instruments or parts of them is a difficult task. Musical instruments are made for artistic use. It is very difficult to define what we expect from them and which qualities are desirable. Our project was aimed at understanding which parameters of musical performance can be suitable to control with a given channel, answering questions like, could that movement be good to control the note's pitch or play chords? We found few evaluation works for the channels we analyzed, and none of them proposed a comparison between channels, and the proposed method was different. To evaluate these channels, we decided to investigate and extract very simple parameters, useful for investigating the quantity and the quality of the information they are able to convey. We have therefore chosen to evaluate movement speed, or more precisely the time to reach a target moving a cursor, and selection stability, namely the amount of flickering and involuntary movement of the cursor while trying to keep it stable. A high score in these two metrics could be very useful in musical interaction, where time constraints are very tight and high precision is required. The first one, movement speed, is a parameter often investigated in the field of human-computer interaction. Fitts' law is a model that forecasts the time t needed to reach and select a target of size w at a distance d. The time required also depends on the empirical parameters a and b related to the used interaction channel. The ISO 94219 standard describes a standard experimental procedure to extract the parameters a and b that describe the interaction channel. The first phase of our experiment is inspired by this procedure. Let's now see how the experiment we performed is structured. We developed an ad hoc experimental interface to analyze 7 channels, gaze pointing along the horizontal axis into formulation, with a raw signal and a filtered signal using a smoothing filter, breath pressure using the breath sensor, and head rotation along the 3 axes. We also added mouse movement to the experiment so that we can compare it to the other channels. The task consisted of moving the white cursor, initially placed at the extreme left of the bar, inside the grey target, whose distance could assume 5 distance values, with random occurrence. Each tester performed 10 measured tests for each channel. Each test consisted of 2 phases. Selection phase, where the tester had to move the cursor inside the target as fast as possible to measure movement speed, immediately followed by the stability phase, in which the tester had to keep the cursor at the center of the target the most stably as possible to measure selection stability. At the end of each session, the tester answered a questionnaire, useful for investigating other parameters and personal perceptions. For each channel, the questions revealed fatigue from use, usability and comfort, precision, the presence of involuntary movements, the perception of speed, as well as the general evaluation of the interaction. 16 able-bodied subjects participated in the experiment. At least 25 to 30 subjects were initially planned, but the outbreak of the COVID-19 epidemic in Italy made it impossible to reach that number. The subjects had no previous experience in using these channels except for the mouse. Let's see the results of the experiment. Regarding the movement speed, the gaze was very fast, with the movement time only weakly dependent on the distance of the target. Its smooth formulation was significantly faster than the mouse. The rotation of the head scored midway between the other 2 channels. The yaw seems to perform slightly better than the other 2 directions. Breath was much slower, with very high variance over long distances. Given the compatibility of the experiment with the requirements to apply the Fitts law model, we proceeded to estimate the A and B parameters through linear regression. ANOVA tests revealed a non-significant difference between the A parameters, while the B parameters detected confirmed the observation mentioned before. Pairwise ANOVA tests, however, showed some non-significant differences between some B parameters. As for the movement stability, gaze pointing certainly suffers from the presence of involuntary high movements, as well as from the high noise of the signal coming from the eye tracker. The head turns out to be a very stable channel, with a stability that approaches that very high of the mouse. The breath turns out to be very unstable, with instability that increases with the distance of the target, and therefore the effort required to maintain a constant pressure. The results of the questionnaires and the personal perception of the testers tend to confirm what has already been detected by the measured performances. Breath and eyes are more fatiguing and less precise and stable. Breath tends to be less comfortable for the proposed task. The eyes also have perceptible involuntary movements, however they seem to be very fast. Breath is perceived as the slowest, as the tests confirm. Let's now discuss the results in terms of ADMI design. The gaze allows for very quick transitions and is probably good at controlling pitch in virtual keyboards. However, it has a limit of 3 to 4 rapid movements per second as mentioned by Ornov. The head is a little slower, but more stable and precise. It is also probably able to make more movements per second than the gaze. The breath pressure was lower to vary and unstable, but it has a natural association with the intensity of the sound. As virtuosos of acoustic wind instruments demonstrate, it is also possible to train it to achieve better results. And so, let's draw some conclusions. We laid the foundations of a method to evaluate ADMI's interaction channels, and we carried out a preliminary experiment to show their potential, analyzing gaze pointing, breath, and head rotation. Possible future improvements include carrying out experiment with a larger sample, taking training and time factors into consideration, as well as obviously including other channels, analyzing new parameters beyond speed and stability, thus including new tasks in the structure of the experiment. And that's all. Thank you for your attention.